Hello everyone, welcome to week 8 of Digital Electronic Circuits at NPTEL, and today we'll be doing some questions that may help you in the assignments as well as in your exam. So let us begin. So the first question is of a ring counter. So in this week, we and also in the coming lots of weeks, we'll be mostly encountering the sequential circuits. And sequential circuits are clock circuits, and uh, counters are an example of counters and registers are example of sequential circuits. So here, first we are dealing with ring counter. So uh, what a ring counter is simply okay. Let's say if we have this ring counter, I'll, so so it is, you can just consider them as D registers, right? So whatever goes in, it keeps on circulating. Let's say if you have, so the first question is, initially you have 1010 as the input, uh, 1010 as the initial state. So it is 1010. Initially it is 1010 initial. Now question is, um, output after so what would be the output waveform? So when the clock is applied here, what will happen? This will circle, right? This will circle like this. So in the next cycle, the output will be 0101, and after that it will be again 1010. So this will keep on continuing 0101 1010. So as you see, the output is what? It is a cycle like this, right? And that is our answer. So the ring counter is nothing. It just keeps on repeating whatever you have stored in these registers. So here 1010 is stored. In the next cycle, this 0 will go to here. And you get 0101, right? So these are, if you remember, these are D flip-flops. And for D flip-flop, Qn plus 1 equals to D. So whatever input you give here, let's say if you give X input, this X input will be passed to Qn as soon as the clock cycle arrives. Okay. So let me see this. Okay. So if you have any questions, please let me know. Feel free to ask on the chat itself, or you can also uh, open your mic and talk. So next we have this question. In the following circuit, consider initial value of all flip-flops to be 0. The outputs will be again 0 after how many clock cycles? So here they are saying initially all are 0, 0, 0 and 0. Okay. Now after how many cycles will we get the output? That so just to note here, if it is 0, here it will be 1, right? It is, if it's Q, it's Q bar. This Q bar is going here. So it is Q4 bar XOR with Q3. So in D1 input is Q4 bar XOR Q3, right? So let us try to solve this. So initially Q2, Q3, Q4. Here 0, 0, 0, 0. Right. So in first clock cycle, what we will have? So let me write Q4 bar also. Bar is 1. So Q1. So in the next cycle, the input here will be 1 XOR with 0, right? 1 XOR with 0 is 1. So I'll have a 1 here, and these will just travel 0, 0, 0. Again, it will be 1. So in the second cycle, again we will have this 1 XOR with 0. So here it will be 1, and this will just shift 1, 0, 0. Again, Q4 bar will be 1. We'll have 1 here in the next cycle. These ones will travel 1, 1, 0. Again, it is 1. The fourth cycle. Now, this is 1 and this is 1. Their XOR is 0 now. We have 0 and we will have 1, 1, 1. Next cycle, 5. This 1 XOR, oh, sorry, it will be 0 now, Q4 bar. So 0 XOR with 1 will be 1 again. 1. These will just shift. Will be 0. 0 XOR 1 will be 1 again. 1, 0, 1. It will shift. It is 0. Now in the seventh cycle, the 0 and 0 XOR 0 is 1. Sorry, 0 XOR 0 is 0. And these will shift. Now Q4 bar is again 1. 1 XOR 1 is 0. 0. So it will be 0, 1, 1. It is 0 again. Now 0 XOR 1 is 1. 1, 0, 0, 1. 0, 0, 0, 0, 1, 0, 0 is 1. 1 over 0 is 1, 1, 11, 0, 1, 0 is 1, 1 XOR 1 is 0. Add another page. 1 XOR 1 is 0, 0, 1, 0, 1, 0, 0 XOR 0, 0, 0, 1, 0 is 1, 1 XOR 1 is 0, 0, 0, 1, this is 0, 0 XOR 0 is 0, 0, 0, 0. Okay, so after 15 cycles, we have reached the same position again, right? So we were 0, 0, 0, 0 initially, and after 15 cycles, we are getting 0, 0, 0, 0 again, right? So the answer is 15 cycles. So I'll just repeat what we were doing here. We had something initially, we had 0, 0, 0, 0 initially. Then the input to it was Q4 bar Q3. I checked at each cycle what is Q4 bar Q3 and then just sent it the as the input to this D1 flip-flop, and here it will just shift. Okay. So now let us see the next question. A 4-bit LFSR with external feedback has the polynomial representation x cubed plus x squared plus 1. Let the LFSR be initialized with 1111. The generated pseudo random sequence has period question mark. Okay. So first of all, LFSR. LFSR is linear feedback shift register. Right. So in the linear feedback shift register, what we have is we have it's here it is given it is a 4-bit, right? So we will have 4 bits. 1, 2, 3, 4. So these are 4 bits, right? It is a register of 4 bits. And what we have is we have some kind of we have always have an XOR gate which feeds into the input, and it can be connected to any of these output of any of these flip-flops, right? So uh, here what this polynomial represents, so let me write it. 1 x square x cube x4. So depending on the number of bits, if we have n bits, we would have had x to the power n. The corresponding polynomial, if we have, let's say, uh, x cube plus x square plus 1, so that means it is connected, the connections are made to the x cube one, and sorry, connections are made to x cube and x square, and the output is fed here. If it was something else, let's say if it was x4 plus x square, then it would have been x4 and x square, and the output of the XOR gate would go to the first to the input of the register. So this is linear feedback shift register. This is the linear feedback, and this is the polynomial equation through which the feedback is fed. Okay. So in our question, x cube plus x square plus 1 is the equation, so it is connected like this. Okay. So they are saying initially it is initialized with 1 1 1 1. Take another page. Okay. So let me call it. Okay. So initially it is 1 1 1 1. Next 1 x square x cube x4. We have input is what? x3 XOR with x2. Or okay. X square XOR x3 is the input, right? So after the first clock cycle, the XOR of x 1 and 1 will be the XOR of 1 and 1 will be 0. So we will have 0 here at the input. These will just shift 1 1 1. Okay. So here what we have to find the clock period. Sorry, the period of the sequence. So we will keep on doing this until we find some sequence. Okay. So in the next clock, so let me write it. It's first clock. In the second clock, again 1 and 1 XOR is 0. These will shift 0 1 1. In the third clock, 0 and 1 XOR is 1. These will shift 0 0 1. Again, in the fourth clock, 0 and 1. 1 and 1 to 0 and 1 XOR. Now 0 and 0 XOR is 0. These will shift 1 0 0. Fifth, 1 and 0 XOR is 1 and 0 XOR is 1, and these will shift 0 1 0. The sixth cycle, 0 and 1 XOR is 1. We will shift here, 1 0 1. And in the seventh cycle, let's see if I made a mistake or not. In the next cycle, we will have again 0 and 1 XOR will be 1 1 1 0. This is what we will have. And in the next cycle, 1 and 1 XOR will be 0. These will shift 1 1 1. Okay. So if we see here, right, this is now repeating, right? Again, if we keep on doing, it will follow the same thing. 1 and 1 XOR will be 0, and this will 0 1 1, and 0 and 1 XOR will be 1. It will be 0 0 1. So you see, this is repeating now. Right. So the period has been asked, right? So it is a period of how many bits? 1, 2, 1, 2, 3, 4, 5, 6, 7. After 7, this same one repeats. So we have a period of 7. Please see the question and let me know your doubts. Okay. So the next question is an 8-bit serial in parallel out shift register is used with a clock frequency of 2 MHz. Initial value of register is this. The time required to transmit the 8-bit value of output is okay. So we have a 2, 3, 4, 5, 6, 7, 8. Initially we have this, and let's say any 8-bit sequence, let's say 1, 2, 3. Let me call it A, B, C, D, E, F, G, H. Let it be an 8-bit sequence. So it is serial in and parallel out. How this will work is, in the first cycle, this H will go in. It will be like H 0 0 0 0 0 0 0. In the second cycle, this G will go in. So it will be G H 0 0 0 0 0 0. Similarly, until all A, B, C, D, E, F, G, H are fed in, right? That is what we have to find, these number of cycles. So here, uh, obviously, this will be 8 cycles, right? N is 8, bits are 8. So N is 8. So we need 8 cycles. And frequency is 2 megahertz clock frequency. So we need 8 clocks, right? So the delay, so time required to transmit, right? That is the delay is 1 upon f into n. That is 1 upon 2 into 10 to the power 6 into 8 gives us 4 microseconds. I hope this is clear. So 1 by f is nothing, just time taken in to transfer 1 bit. And you should transfer, and that is 8 bits we have to transfer. So time of 1 bit into 8 gives us total time to transfer the output. Let us go to the next question now. So next question is Johnson counter. So Johnson counter is, we have already encountered it once. So Johnson counter is again a serial shift register, but with input is the Q4 bar, right? Q4. So it will be like this Q1 will go to Q2, will go to Q3, but this Q3 will go to Q4, and but we will have Q4 bar here. Okay. So initially it is this, consider delay from input to output of flip-flop is 1 millisecond, after how much time the output will be all zero again. So first for that we need to find out in how many cycles the output will be zero again, right? So Q1, Q2, Q3, Q4. Initially all are 0, 0, 0 and 0. Q4 bar also we have this one. So right, so in the first cycle this this will go here, this will go here, this will go here, and this one will come here, right? Q4 bar will be 1 again in the next cycle. So it is, let me write it like this. First, the second cycle, this one will come here, this one will go here, this must go here, this will go here, this will 1 again. Third cycle, this one will come here, this will go here, here, and this will shift. Again, Q4 bar is 1, which will be again the input here, and these ones will shift, right? Now it is 0. Fifth cycle, it will be 0 will be input, these ones will shift. 6th cycle again 0 is the input. 7th cycle we have 0 input and these zeros will shift. In the 8th cycle we have 0 0 0 0 again, right? So it took total 8 clock cycles to go from this state back to this state. Took 8 cycles, right? And given time period of each delay of each flip-flop is 1 millisecond. So it will take total 8 into 1 millisecond, that is 8 milliseconds. Simple. So the only thing to note in Johnson counter is Q4 bar goes as the input. In the ring counter, we just this Q4 would have passed, right? This would have gone. But in Johnson counter, Q4 bar goes. Okay. Let us see the next question now. Okay, so I'll wait a few minutes for you guys to do this first because it is easy. We just saw a Johnson encounter. Suppose 4-bit ring counter is initialized with sequence this. What is the following value convert will not occur through its counting states? So we have this as the ring counter, right? So let me make it again. Right. We had this, but here Q bar was going here. Q1, Q2, Q3, Q4. This Q4 bar is the output, right? They're saying initially we have Q1, Q2, Q3, Q4 as 1, 1, 1, 1, and this corresponds to in the first cycle, right? Okay, whatever is the cycle. So this corresponds to in binary it is what? 15, right? So in the next cycle it means like Q4 bar will be 0. So this, let me not write Q4 bar, it is understood. So next 0 will be here and these will shift 1, 1, 1. So this is what? 7. So after this complete cycle, again when we get 1, 1, 1, 1, it is 15. What are the all these kind of numbers covered? Which number is not covered? That is the question. So I'll wait a few minutes for you guys to attempt it. Okay, so I hope you have tried it. Let me solve it now. So in the next cycle, this Q4 value will be 0 again. This will shift 0, 1, 1. This is what? 3. The next cycle we will have 0, 0, 0, 1. That is 1. The next cycle we will have 0, 0, 0, 0. That is 0. This. The next cycle Q4 bar will be 1, 0, 0, 0. That is 8. Next cycle will be 1, 0, 0. That is 10. Oh, sorry, 12. Next will be 1, 1, 1, 0. That is 14. And next will be 1, 1, 1, 1. Right? Which is 15. So, right, we are just transmitting after each cycle. Q4, if this is Q4, Q4 bar, that is 1 is being here, and these all just shift. So the numbers that are covered are 15, 7, 3, 1, 0, 8, 12, and 14. If we see which numbers are covered, 7 is covered, 3 is covered, but 5 is not covered, right? So the answer is 5. 5 will not occur in the context states. Okay, let us see the next question now. Which of these two LFSR circuits, circuit 1 and 2, can generate maximal length sequence? Okay. For that, we need to understand first what is maximal length sequence. So we have this LFSR. Okay. So a maximal length sequence LFSR is the one which produces uh, produces an M sequence and bit sequence, and it cycles to all 2 to the power M minus 1 states. Right. The shortcut to determine which are the maximal length sequences, all the sequences which have the polynomial x to the power n plus x plus 1, right? Sorry, n plus x power n 1 plus 1. This is the general rule for maximal length sequence. If also, if n is even, then maximal length sequence is also given by LFSR polynomial to power n minus n plus x to power sorry x to power n plus x to power n minus 1 plus x to power n minus n. That is 1. That is x to power n plus x to power n minus 1 plus 1. So these for even, so here we have 4 bits, right? So we will have x to power 3, sorry, x4 plus x plus 1 and x4 plus x cube plus 1. These both will generate maximal sequence. Maximal length means all to our m minus 1 states are covered in the sequence. So here we have x1, x2, x3, x4. So here we have x4 plus x plus 1. Here we have x4 plus x cube plus 1. Right? And these both are maximal length sequence. This is, and this one is only when n is even, and this is for all n. So the answer is, which can generate maximum length sequence? Answer is both. Right? Please see it again once. Okay. So let us see the next question now. You have to find the polynomial here, right? So just first step is write the bits x1, x square, x cube, x4, x5, and whatever are connected to XOR, x5 plus x4 plus 1 is the polynomial, right? But now is it primitive? Oh, sorry, it is maximal. We saw here, right? Xn plus xn minus 1 plus 1. Here n is equals to 5. So x5 plus x4 plus 1. So should it be yes? No, because it has n is odd. So we only will deal with the general representation for maximal length sequence of polynomial is x to power n plus x plus 1. And this is not the case here. So the answer is x5, x4, x1, and no. And this is the answer. Please see both of these again once, these rules again. So the next question here is, uh, okay, let me give you a question for LFSR. It's not here. Okay. Question is a 4-bit SAR with external feedback has polynotation x cubed plus x square plus 1. The generated, have we done this? No. The generated pseudo-random sequence has period. So what this means is, so PQRS, we have x1, x2, x3, x4. We have x square plus this, right? So you have to find the period for this circuit. So please take some moment and try to solve this. Okay. So assume it is initialized with 0, 0, 0, 0. We had already done a question with 1, 1, 1, 1, right? Yeah, we had done it with 1, 1, 1, 1. Now do it with 0, 0, 0, 0. The same question, just initialization condition is 0, 0, 0, 0. Okay, so let us now see. I hope you are able to do this, but I'll just do it with you. QRS initially 000, and let's first cycle we will have these will just shift 000, and we have what this is x1, x square, x cube, and x4. We have the XOR of these two, right? So that is XOR of these two. XOR of these two is 0. We go here 0. Sorry. Second cycle again. That is ticket 1. Initialize it with 0001. 1000. So I'll repeat it. Initially it is 1000. After the first cycle, this will shift 100, and here we will have XOR of these two. XOR of 0 and 0 is 0. This will again shift 0. So we don't know the initial, right? 0 1 0, and XOR of 1 and 0 is 1. The third cycle, these will shift 1 0 and 1. XOR of 0 and 1 is 1. Fourth cycle, shift 1 1 0. XOR of 1 and 0 is 1. Fifth cycle, XOR of 1 and 1 is 0. 1 1 1. Sixth cycle, XOR of 1 and 1 is 0. This is 0 1 1. Seventh cycle, XOR of 1 and 0 is 1 0 0 1. Eighth cycle, XOR of 0 and 0 is 0. It will be 1 0 0. Now you see this is repeating, right? So it has repeated how many states? See, it has repeated 1 2 3 4 5 6 7. Then we again get this first state back. So it has a sequence length of 7. So period is 7. Right? Is it clear? If initialize it with 1000, we'll get this. Okay. So let us see the next question now. A delay line circuit is to be generated to create a delay of this much between input and output. How many number of flip-flops are required in a CISO register to produce the required delay? Okay. So this is easy. Right. So we need a delay tau of 64 millisecond. Clock frequency f is 1.25. We know tau is 1 upon 2n tau PD. Sorry, f is 1 by 2n tau PD. So n is what we need to find, right? N is the number of stages. Number of stages in oscillator, or here it is n equals to number of flip-flops. So n will be 1 by 2 f tau PD. It is 1 by 2 into f is 1.25 10 to the power 6 10 to the power 6 hertz into 0.64 into 10 to the power minus 3 seconds. So if you solve this, we should get n equals to 800. So we need 800 flip-flops to generate this much delay, right? What this simply means is that FC is 1.25. So going from when the input shifts from here to here, from this flip-flop to this, from one flip-flop to the next flip-flop, it takes 1 upon f time, right? 1 upon 1.25 megahertz, the time taken this, right? So to generate total this much delay, we need how many number of flip-flops? So we need to find n into 1 by 1.25 into 10 to the minus 10 to the 6 is 0.64. That is what we are doing here. Okay, so it is easy. Just remember this: f is equals to 1 by 2n tau PD, where n is the number of stages ending oscillator or number of flip-flops. Ring oscillator, what is meant? Number of inverters. This is a ring oscillator, right? N is odd in ring oscillator. Okay, so next question. So initially, okay, so initially they're saying we have 0, 0, 0, 0, 1, 0, 0, 1, and here we have 1, 0, 0, 1, 0, 0, 0, 1. We have to find the find what is in register A after 8 clock cycles. So input to register A is the sum. What is being summed? This bit and this bit is serial out, right? So whatever will be the output from here will get summed. We will generate sum and carry is connected to a toggle flip-flop, T flip-flop. So in a T flip-flop, what we have, right? When T equals to 0, Qn plus 1 equals to Qn, T equals to 1, Qn plus 1 equals to Qn bar. So whenever this Ci will be 1, this output will flip. Okay, so let us try to solve it. Let us see. Okay, let us try to draw it here itself. So it is easier for us. Yeah, right. Block AI, BI, CI minus 1, SI, CI. Okay, so initially in the first block we will have 1 and 1. This one and this one will come here, right? We'll have 1 and 1. Okay, sum of so initially CI is 0, sum of 1 and 1 is 0, and carry is 1, right? Sum of 1 plus 1 plus 0 is 0, and carry 1. Now in the second cycle, now since the CI is 1 now, in the next cycle this will toggle. It toggles, that means this flips, right? It means t equals to 1, it will flip this CI. CI is Q. Okay, so we know what is CI now. So next we will have here is 0 and 0. These will be the input here, right? This 1 are already gone. This 0 and 0 will come now. So we will have 0 0. So 0 0 1 sum is 1 with carry 0. Okay. So in the third cycle, this 0 and this 0 will come. 0 0, and CI will not change, right? It won't flip. It will keep on being 1 until unless we have a uh, we have another toggle. Until unless this toggles with another 1 here, it will not flip. So it will continue to be 1. Sum is again 1 and carry is 0, right? So in the next cycle, now we are done till here, right? So we have 1 and 0. Yeah. So in the fourth cycle, we have 1 and 0. The CI will remain same. So that is not flipped, and 1 plus 1 is again 0 with carry 1. Okay, now we have a carry 1. Now this will flip to 0. And the fifth cycle, we have so first, second, third, fourth, fifth, sixth, seventh, eighth. We will definitely lead 8 cycles, right? 6, 7, 8. In the fifth cycle, input is 0 and 1. Sum is 1, carry is 0. So this will not flip now again, it will remain 0. In the sixth cycle, input is 0 and 0. Sum is 0, carry is also 0. So this will, since it is 0, it will not flip and it will be 0 again. So in the seventh cycle, we have 0 and 0 again, 0 and 0. Sum is 0, carry is also 0. Since this carry is 0, it will not flip, it will be 0 again. Now it is 0 and 1, and sum is 1. Carry is 0. Okay. Now if you see this, what is happening? This SI is only going as input to this. So this SI is actually, so what we will have new Input to A, new A. Okay. Now A will be filled with 0, 1, 1, 0, 1, 0, 0, 1. This will be the new values in A. It will be written the same thing clearly now. 0, 1, 1, 0, 1, 0, 0, 1. So this is the this is what matches, right? Please see it again. So I'll repeat what we were doing. We had this initial inputs. Every clock cycle, this one by one, these will go out, and whatever the sum will be filled back in. So if initially you have this 1 and 1, 1 and 1, Ci is 0 initially, 0. Sum is 1 and 1, 1 plus 1 plus 1 plus 0 is 0 with a carry of 1. So now this 0 will go at the back here, right? And since carry is 1, this carry is connected to a toggle flip-flop. And in a toggle flip-flop, whenever t is equals to 1, the output is qn bar. Qn was, this is Ci is minus 1 is q, so output will flip to q bar. 0 will flip to 1. This is what we were repeating. Please see it once, then we will move ahead. Okay, let us see the next question then. In the following circuit, the desired frequency of the output signal is 10 kHz. How many numbers of inverters M are required to be cascaded to achieve the desired specification? TP of each inverter is 5. Okay, so we already know, right? F equals to 1 upon 2n tau PD. Like n is the number of inverters. So we have to find n. So we have to find n. Tau PD is given to be 5 nanoseconds, right? They are saying signal at output is 10 kilohertz. Now, so but we need the frequency here, right? Not here. So how does the frequency travel here? That we have seen, if here it is f, here it will be f by 2, here will be f by 4, right? So f by 4 is 10 kilohertz. So f is 40 kilohertz, right? So f is also known now, f equals to 40 kilohertz. So n is 1 upon 2f tau PD, 1 upon 2 into 40 into 10 to the power 3 into tau PD is 5 nanosecond, 5 into 10 to the power minus 9. It is 10 to the power t to t. It is 2500. Right? So we need 2500 n according to this formula. But actually, we are making other what we are making inverters. We need number of inverters, but we know for a ring oscillator n should be odd, right? So need 2499 inverters. Why n should be odd? So if we have just this, let's say if I have a 0 here, it will be 1 here, it will be 0 here. So it will just store this. But if I need to flip it again and again, then I need odd. It will be, if it's 0 here, it's 1 here, it's 0 here, it's 1 here. Now this 1 will go here, 1 here, 0, 1, 0, again 0, 1, 0, 1. This is how it will oscillate and how it will work as a clock. Right? A clock is an oscillator. Right? Clock. That is why the answer is 2499. The next question now. You have an 8-bit Johnson counter. So initialize it 0000. What is the mean value in the decimals representation? What is the mean value for its counting sequences? Okay. So first, how many number of states will it have? If it's 8-bit, it will have 16 states, right? So if we start with 0000, okay, let me write it better. Okay, so you remember, right? What is Johnson counter? Q1, Q2, Q8. Here, Q8 bar output will go here as an input. Okay, so it is 0000. Yes, Q8 bar. It's Q1. So Q8 bar will go here. Q8 bar is 1. These will just shift 000000. Right. This was 0. This is what? 128 in decimal. Okay, so let's keep on doing this. It will be 1100000. It is 192 111 00000. Please do it with me. 224 111 000 plus 240 111 000 248. I'm just converting binary to decimal. 1100 252 1111110 254 111111 255. Now it is 1, so its bar will be 0, so 0 is input now. This will shift. It is 127 001111. So this is 63. We'll have 0001111 31. Right? 0. Having more lines. 0001111 31. We'll have 15. This 15, right? 0000111. That is 7. 0000111. Sorry, 3. And 0000001 is 1. These are all the decimal numbers. Now we have to find, what do we have to find is mean. The sigma of these numbers upon 16. We have total 16 states, right? 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. After this again we'll have same 0, 0, 0, 0, 0, 0, 0, 0, what we started with. So we will have to do is sum of 128 plus 192 plus 224 plus dot 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 till 1 upon 16. Please do this sum. So the sum will be 2040 upon 16. So the mean will be 87.5. All the answers are very close, so you need to be careful while solving these. Hope it is clear. It was very simple question. We had already seen many times. So let us see the next question. So again, we have parallel out 4-bit serial in parallel out shift register. Input bit sequences 101. Okay. Initially it is 0000. We have input 1101 is to be entered. The output after 2 clock cycles. Please do it. It's very easy. I'll wait for you. Okay, so let us do this. In the first cycle, this 1 will go as input and these will shift 000. Second cycle, this 0 will come 100. So this should be the answer. And in the third cycle, it will be 0 0 1 0. Fourth cycle will be 1 1 0 0 0 1. Right? In the second cycle, this is the answer. Yeah. Another question. Similar question initially is set to 1111 and the data is 1010. After 3 clock cycles, what will be the output? Okay, so let us do this. In the first cycle, the 0 will come here, 0, this will shift, 111. Second cycle, this 1 will come, 1, 0, 1, 1. Third cycle, this 0 will come again, 0, 1, 0, 1. Fourth cycle, this 1 will come, 0, 1, 0. Now the data is fed and we have been asked first, 2, 3, third cycle, 0, 1, 0, 1. Last question is this. Please solve it. I'll give you some time. Okay. This is again kind of LSFR, but here we have XNOR now, right? So we have 1100. These two are ignored. So XNOR of 0 and 0 is 1. These will shift 1, 1, 0. This is first cycle. Second, third, fourth. XNOR of 1 and 0 is 0. So XNOR of 1, 1 and 0 is 0. These will shift 1, 1, 1. XNOR of 1 and 1 is 1. These will shift 1, 1. And again, XNOR of 1 and 1 is 1. These will shift 1, 0, 1. This is the answer. At fourth cycle, we have 1, 1, 0, 1. Please see if you have any issues. Okay, so this is all for today. If you have any doubts, you can also email me or uh, write in the YouTube comments. I'll reply to your queries, and we'll see you again in the next week. Okay. Thanks for joining.